Howdy guys, welcome to the lecture on unions and intersections. I'm really excited about this. I just finished putting this together for the fall 2020 course. With the new textbook, we're going to be looking at probability and unions and intersections and everything a little bit differently than what we've looked at in the past. So I'm looking forward to going through this. So by the conclusion of this lesson, you're going to be able to define what a union is, calculate the probability of unions, and to define intersections and calculate the probability of intersections. So this is a really useful slide that I would encourage you to just keep around, that you'd be able to refer back to when you see particular terms, so on and so forth, that you would go back to this slide. Also, another location where it is on the Unit 2 formula sheet. I have all of this listed on the Unit 2 formula sheet as well. But when you see certain notations, I want you to know what those notations mean. So this is a really good slide to refer back to. So you can pause this for a minute and look through all this if you want, but we're going to go through all this as well in the subsequent slides. So when we have probability, what we're talking about is what is the likelihood of an event or multiple events occurring. In the last lecture, you looked at what an event is, what a sample space is. You looked at an outcome. You looked at an experiment. And so when you have all those different pieces of information, a lot of times you actually have two different events, and you have a question of, can this event occur and this event occur, or what's the probability of either one of these events occurring? And so when you have those types of questions, it's really good to know how to calculate the probability of one, both, neither, one of the other events occurring. And so two terms that are really important to know, or rather three terms. We have mutually exclusive events, which are events that cannot occur together. In other words, you cannot be a freshman and a sophomore. You can either be a freshman or a sophomore. And so if I were to ask, what's the probability of you being a freshman, you might say 30%. What's the probability of you being a sophomore? You might say 25%. What's the probability of you being a freshman or a sophomore? We'll just add those two together, which we'll get to that in a little bit. But that would be 55% is the probability of you being a freshman or a sophomore. So the other one is not mutually exclusive, is when multiple events can occur within an experiment. In other words, what is the probability of you having, let's say, what is the probability of you being an accounting major? And you might have a certain percent chance, a certain probability of being an accounting major. What is the probability of you being an MIS major? Well, you've got a certain percentage chance of that as well. And what is the probability of you being both an accounting major and an MIS major? Well, that's certainly possible because we do allow double majoring in the business school. And so event A and event B can occur at the same time, so those would not be mutually exclusive events. Often individuals confuse mutually exclusive events with independent events, or independence. In other words, the occurrence of one event has no impact on the probability of the occurrence of another event. For instance, if we look at the probability of an individual being an accounting major and an MIS major, are those two events, are they independent of each other? Does one impact the other? And we could say maybe a little bit, but I'm not really sure. So maybe those aren't completely independent. Or, another example is, what is the probability of me wearing a pink shirt and Adidas shoes? Two completely separate things. Or better yet, what's the probability of me wearing a pink shirt and what's the probability of me driving to work today? Two completely separate, independent things that occurred, independent events. They have no relation to one another. One does not impact the other. It does not influence the probability at all. And then dependent would be, when they are dependent on each other. For instance, what is the probability? Let's see here. What's a good example? What's the probability of me wearing pink goes with blue? Me wearing a pink shirt, and what's the probability of me wearing blue pants? And pink goes really good with blue, so therefore it influences the probability, and they're dependent on one another. And so one is dependent on the other. It impacts the probability of another event. It's not saying that it has to occur in order for the other one to occur, although that can be the case as well, that one has to occur in order for the second one to occur. So we have, like I said, unions, and we also have intersections. Okay, so we're looking at what is the probability of an event occurring or another event occurring. So what is the probability of either one of these events occurring? Either event A or event B. And so when we do this, that's referred to as a union. So an online t-shirt company uses a software program to provide estimated shipping and arrival dates for their customers based on current production queues. Based on a sample of 4,000 shipments, the company tracked the probability of occurrence of the shipment arriving early, on time, or late. Okay, so looking at this table below, this right here is referred to as a probability distribution. Or probability table, and so you have the event, you have the number, you have the probability of occurrence, and then right here you have 500 divided by 4,000, which is the relative frequency. So we've got 500 divided by 4,000. This would be 3,200 divided by 4,000, which would be the probability of occurring. In other words, this is inferential statistics. We are taking 3,200, dividing it by 4,000, and we're saying, based on that information right there, we are expecting this to occur 3,200 out of 4,000 times in the future, give or take something that we're going to go over a little bit later. Then what's the probability of it being late? And that is 300 divided by 4,000. Now, we actually have the ability to just add these together, and the reason why is because they are mutually exclusive. So, for instance, what is the probability of it arriving early or on time? What is the probability of having the union of the two of them? All that you have to do is add up the probabilities together, so it'd be 9.25. Or what is the probability of it being early or late? Just add up the two probabilities, and so that'd be 0.125 plus 0.075, which is right down here. Probability of A or C equals the probability of A plus the probability of C equals this right here, which would equal 0.2. Now, what's really important is when you look at this probability table, probability distribution, all of these probabilities have to add up to 1. So you notice that they all add up to 1 because the probability of any of them together would equal 1, or all of them together would have to equal 1. And that's called collectively exhaustive, which I believe we'll go over that a little bit later. But when you talk about every single possible outcome, and every single possible outcome is listed, then they will all be listed and they will all add up to 1. Okay, so once again, we've got unions, and then we also have intersections. So on the left-hand side, we're going to have unions. On the right-hand side, we're going to have intersections, which is kind of funny because you actually have to understand intersections in order to be able to really fully understand unions. So unions are, like I said, used to add the probabilities of multiple events occurring, and you really need to look for the word or. Sometimes individuals refer to this as the rule of addition, but we're going to refer to it as unions. And so a union is when you have multiple events occurring, and you can add the probability of those multiple events together to find the union of those events, or the probability of multiple events occurring, either A or B. A little trick that I like to use, well, let's get to intersections in just a minute. So, or includes event A, event B and event A or B, or A and B. So it can include event A all by itself. So in other words, event A happens all by itself, event B happens all by itself, and event A and B happen together. And so that's what a union is. An intersection is only this little middle part. Only this little middle part, that is an intersection. And so you've got the intersection, which is right there, and then the or includes everything. So the way that I like to look at it is it includes A, and it includes B, and you've got this U, it includes any combination of A and B together. So you can dump in any combination of A and B right in there, and that's what it includes. And intersection, it's upside down, and so it only includes the intersection of A and B. It doesn't include A, it doesn't include B, it only includes the intersection of A and B. And so I look at the U and I say, oh, you can fill it up, it's a lot bigger, with everything else that's associated with A and B, and then the intersection, like I said, it's upside down. That's the showing the intersection. You can only include the intersection of A and B, nothing else is included. And so we've got this formula right here. The union of A or B equals the probability of A plus the probability of B minus the probability of A and B. So you're probably thinking to yourself, why do we have to add up the probability of event A and the probability of event B, but then we subtract the intersection? And the reason why is because if you add up the entirety of probability of event A and the entirety of the probability of event B together, you're actually including that intersection twice. You're including that intersection twice, so you have to remove the intersection one of those two times. And so that's why you have to understand the intersections in order to be able to understand unions. Okay, so it does not include if neither event occurs. Okay, so it only unions only include if event A or event B occur, or event A and B occur, but it doesn't include if neither occurs. So that's really important. These don't have to add up to 100 if it doesn't represent everything. Okay, and once again, probability of A, the union of A and B, or A or B, equals the probability of A or B occurring. And then the intersection, once again, this is the notation, and it's the probability of both A and B occurring. Okay, and then if the two events are mutually exclusive, you don't have to worry about subtracting this middle part because there is no middle part. There is no intersection. If they are mutually exclusive, this is really important. If events are mutually exclusive, there is no intersection. There is no intersection if the events are mutually exclusive. Okay, so let's look at an example. A sample of 200 tourists in Waco shows that 120 went to Magnolia Silos, 100 visited Baylor, and 60 visited both. Okay. And so we've got event A. Event A is the probability of individuals visiting the silos, which equals 120 out of 200, which, once again, this is dealing with empirical probability. We're looking at past events, and based on past events, we are determining the probability. So we've got event B, or event A is that they went to the silos. Event B is that they went to Baylor. And then as long as the two events are independent, you have actually the ability to use this fun little multiplication formula and just multiply the two of these together to find the intersection. Once again, that is only if the events are independent. In other words, the probability of silos does not influence the probability of an individual going to Baylor. And the probability of an individual going to Baylor does not influence the probability of them going to the silos. So if they are truly independent, all that you have to do is multiply the two of these together to get that middle section right there. And we're going to be dealing with a lot of independent events. Okay, so outcome, once again, we're talking about the outcome of A and B equals the probability of silos A and the probability of the silos and the probability of Baylor. So what's the probability of them being going to both the silos and Baylor? And that is 0.3. 0.3 equals 0.6 multiplied by 0.5. So notice the probability of A, which is event A, multiplied by the probability of B, event B, Multiply those two together, and you find the joint probability, or the intersection. The intersection, or the probability of the intersection. Okay, so outcome of the probability of A or B. In other words, it could be, they could go to the silos, or they could go just to baler, or they could go to the silos or baler. And what we're going to do there is the probability of A, which is 0.6, once again, the probability of them going to the silos, plus the probability of them going to baler, which is 0.5. So you add the two of those together, and then you subtract the intersection right there. Remember, we're subtracting it one time, or else it would have been included two times. So we're subtracting it one time, so that way it's only represented once. And that's going to give us 0.8. So what is the probability of them going to the silos or going to baler? In other words, they're going to at least one of those two places. What is the probability of the silos or baler? Them going to the silos or baler, and that's going to be 0.8. Now, if we didn't subtract this 0.3, it would have been 1.1, right? And the probability of them going to the silos or baler should definitely not be 110%. So the probability of them going to the silos or baler is 80%. But notice here, it is 80%, which means that there is the probability of them going to neither the silos or baler. Neither the silos or baler. So that means that 80% are in this white circle thing here. And if there's 80% in here, and this right here, the sample space, is this brown, that represents every single person that visits Waco, that means that there is a percentage of individuals that visit Waco but do not visit the silos, and they do not visit baler. And so that's going to be 1. 1 minus 0.8, which is going to give you 0.2, is neither the silos or baler, because if 80% is in here, that means that, and this represents 100%, that means 20% is in neither the silos or baler, which I think we're actually going to do that, yep, right here. So, once again, this is really important. When you were talking about a probability distribution has to add up to 1. Has to add up to 1. And so with the previous information, we don't have the ability to make a probability distribution. Okay, so if we look at either the probability of either A or B, in other words, we have A plus B minus A times B, okay, which equals 0.8. That's the probability of them going to the silos or going to baler. What's the probability of them going to the silos? 0.6. What's the probability of them going to baler? That's 0.5, and so we've got 0.5 plus 0.6 plus 0.8, which gives you 0.9. Even if you were to change this and you were to say and put a union there instead, let's do this. What's the probability of this? 0.3. Let's see here. 1.4. So the probability of that intersection, the silos and baler, plus silos plus baler, that's not going to work either. You've got to have every single individual part represented in there in order for it to add up to 1. In other words, we're trying to compose this entire circle. We're trying to represent every single slice of this entire circle in a probability distribution. Okay, so we've got a probability distribution, which this fun little apostrophe means only. Okay, so only A, what's the probability of an individual going to only the silos? Well, in order to do that, you just have to take 0.6 A minus the probability of A and B. So in other words, A minus the intersection. So A minus the intersection equals 0.3. And then what is the probability of them going to only baler? That's going to be B, the probability of going to baler, minus the probability of going to the silos and baler. So in other words, minus the intersection, which gives you 0.2. So only baler is 0.2. And then both, what's the probability of them going to both the silos and baler? So we've done this portion. We've done this portion. Now we're doing this portion right here. So the probability of silos and baler equals A multiplied by B, which is this middle section, which is 0.3. And then last but not least, what is the probability of them going to neither the silos or baler? So all that we've got to do is do 1 minus either, which we've got either right up here. So 1 minus all of this, which gives you 0.2. And so we've got this section represented, we've got this section represented, this section, and this section, and you add all of those individual sections together, and they all add up to 1. So this right up here is not appropriate, this down here is appropriate. And when you're parsing everything up, it's really important to understand that you've got to represent every single part, but don't ever represent any part more than once. Okay, and that's how, with a probability distribution, how you need to set that up. Okay, well, and we've already done this. It's called the complement rule, but we're going to use the complement rule now and really explicitly refer to it as the complement rule. Right here, we already did it, right? Sorry, this is what happens with a scroll mouse. We used the complement rule right down here when we said neither. We did 1 minus either. Okay, right here, the probability of A not occurring, in other words, this little apostrophe, probability of A not occurring equals 1 minus the probability of A occurring. So in other words, if the probability of A is 0.125, then the probability of A not occurring is going to be 1 minus 0.125. So that would equal 0.875. Okay. What is the probability of B not occurring? That's going to be 1 minus the probability of B occurring, so that would be 1 minus 0.8, so that would be 0.2 is the probability of B not occurring. Okay, and then what's the probability of C not occurring? Same thing, 1 minus 0.075, so it's going to be 0.925. And so you can also use the complement rule. What's the probability of A or C occurring? Is the probability of B not occurring. So in other words, if you're trying to find what's the probability of A or C, you could essentially just say what's the probability of B not occurring. So you could do 1 minus 0.8, which gives you the same as probability of A plus, or the probability of A plus C. Or A or C, because these are mutually exclusive. Cool. Yes. Intersections. So this is really important too with a term called conditional probability. Conditional probability is when, like I said, events are dependent on each other. Some events are not dependent on each other. Like for instance, this is an example. A survey by the American Automobile Association, AAA, revealed that 60% of its members made airline reservations last year. 2 members are selected at random. What is the probability that both made airline reservations last year? And the probability of one does not impact the probability of the second. And you see right here, these are subscripts. The subscripts, it says 1 and 2. So we're going to refer to as the probability of random member 1 and the probability of random member 2 equals the probability of random member 1 multiplied by the probability of random member 2, which equals 0.6 times 0.6, which gives you 36. Once again, they have to be independent for this to work. Okay, so you can just literally multiply them together if they are independent. If they are not independent, it's slightly different. Okay, so conditional probability is the probability of a particular event occurring given that, okay, that's how you say it. What's the probability of B occurring given that that A occurred? Okay, so conditional is represented by probability. What is the probability of B occurring given that A occurred, or the probability of B given A? So, and to do an intersection with conditional probability, like for instance, what's the probability of A and B occurring? That equals the probability of A multiplied by the probability of B given A. In other words, you've got to adjust the probability of B given that A already occurred. So here's an example of that. And we've got these intersections right here. Once again, you've got these subscripts down here. What is the probability of A and A sub 1 and A sub 2 occurring? In other words, we're going to read this right up here. A company is conducting an interest group study to see if children prefer vehicles or animals. If 2 children are put in a room with 6 vehicles and 6 animals, if the first child grabs a bear, what is the probability that the second child will also grab a stuffed animal? So we have the probability of A sub 1. In other words, the first child grabs a stuffed animal, and the second child also grabs a stuffed animal. And you notice right over here, event A is child grabs a stuffed animal. Event B is that child grabs a vehicle. So this right here is event A for child 1. This is event A for child 2. Down here, this would be event A for child 1. This would be event B, that should say, for child 2. Sorry, sometimes I forget. There we go. B for child 2. And so we've got probability of A. First of all, what is the probability of A for child 1? Well, you look at this and you see, okay, they grabbed a stuffed animal. Well, that's 6. There's 6 stuffed animals out of a total of 12. So 6 out of 12, which is 0.5. Okay, so 0.5 multiplied by probability of A sub 2 given that A sub 1 happened. Well, probability of A sub 2 given that A sub 1 happened, well, now there's only 11 items left. There's only 11 items left. So what's the probability with 11 items left that the second child is going to grab a stuffed animal? Well, that's going to be 5 out of 11, because not only are there only 11 items left, there's only 5 stuffed animals left. So the probability of A multiplied by the probability of probability of A sub 1 multiplied by the probability of A sub 2, given that A sub 1 happened, equals 6 over 12 multiplied by 5 over 11, which gives you 0.227. Going in a different direction, what's the probability that the first child is going to grab a stuffed animal, and the second child is going to grab a vehicle? And the way that we would do that is the probability, what is the probability of the first child grabbing a stuffed animal, which is not dependent on anything, so it's just 6 out of 12 again. And then given that the first child grabbed a stuffed animal, or what is the probability that the second child grabbed a vehicle, given that the first child grabbed a stuffed animal? And so there's 6 vehicles divided by a total of 11 items that are left. So that's 6 over 11, which is a little bit different than the 5 over 11 previously. And so that equals 0.273. And so this right here are, this is intersections with conditional events. So that's really important to know how